Okay, so good morning to you all. So I'll be discussing today about the GIS data models. So this is basically a layout. So I'll just try to give a case where I'll just try to explain why we need a GIS data structures. Then we'll also see a few example of how actually the data structure is being represented. That's abstract representation of those data sets. Then I'll also try to touch upon a few example or few GIS databases which is being used. Along with that, I'll also touch upon a little bit of a spatial referencing model and the currently available open standard models. So let's take an example of what kind of GIS analysis we do. So this is a simple example where we are having a two place designated with A and B. And A is a place of starting point, that's basically Indian Institute of Remote Sensing, and B is basically a destination points. So someone, if he wants to know how can we reach from A to B, then this kind of analysis is possible with the help of GIS. And generally the such user requirements and questions are being actually solved under the GIS analysis examples. So if this such question is being imposed, then in reality, if you see the world, it looks like quite cluttered. So you are having a lot of informations, like in this case, a satellite imagery, which houses, road networks, a lot of vegetations. So there are a lot of information is available to extract or to carry out the kind of GIS requirement, whatever we had. We need to have some kind of simplification of this whole representation. So whatever reality we see where the lot of cluttered information is there, so what we do is basically we extract only relevant informations and we use it for analysis. So in the right side, whatever we see for to solve a simple questions to find out the distances between a location A to B, we need only a road network. So other details like vegetations and the houses can be masked uh, for analysis purposes. So if you're having such kind of use cases where a few GIS requirements are there and that needs to be processed through GIS process model. So in this case, basically you're finding a path between A to B is actually falling under the process modelings. Then whatever solution which we get, again we represent it back to the user. So these kind of use cases are there. To solve these use cases, generally what we need to do is that we need to have a proper organizations of the data sets. So if any machines, if you want some data to be processed by any machines, then in that cases the data has to be organized in an appropriate way. If data is not organized properly or there is no structure in your data sets, then the analysis can be very difficult. So GIS data models, whenever we say, it basically deals with the kind of data organizations which we need to carry out any kind of GIS processes. And that's a basic one of the important component where we convert all those requirements. So like in this case, we need to have road informations and details. So that informations we will be just trying to organize it. So to do an organizations, we first need to understand how do we carry out the analysis. So if you just have a requirements to find out, so generally people should know, anyone who is answering it. So let's say you are on the road and you ask someone's that, can you please tell me how can I reach from IRS to a clock towers? So in this case, the information is that you're having a starting point and locations, and then based on the persons who is going to answers their experience, they will give you an answer like you take a left, a right turn, go straight by this much kilometers and so on, and finally you'll be reaching it to main road like Rajpur Road and so on, and then you need to travel a bit, and then accordingly it will take a time. So generally, if anyone will tell you, so to give your informations, he will sometime he may say that go from location A to B, that is from IRS to a Kalidas road, you need to take a New Kent road, and then you will be reaching a clock tower via Rajpur road. And approximately it will take 8 to 10 minutes. So initial information, you're having what exactly is the starting point and end point, and based on the people experience, you'll be getting an answers like this. But to carry out the analysis, similar kind of analysis, if we just replace that human persons with the machines, then we need to, the same information first needs to be fed into the systems in an appropriate way. So for that, we need to have some kind of agreement between the understanding of human and as well as the kind of data which will be represented by or inside the machines. So we are having a location A, so generally it's called a point geometry, and generally whenever we say in machine terms point geometry, it means like it needs to have a coordinate locations. So like in this case we are having two locations, so that's the starting point and end point. Then we also need to know, like we need to provide a path. So it means like we need to have a set of line segments, that's basically called line geometry. And each of those geometry will have a few attributes like its name, what exactly is the name, how much time it takes to reach from location A to B. So all these information has to be organized in a systems, and then finally based on these organizations we can use a few GIS analysis tools to find out and get a result, like we had a path and then how much time it will take and so on. So those kind of answers can be you can get it from the machines. So for GIS, in case of GIS, basically the data sets which is being represented are in term of point geometries. There are few attributes informations, that's the name of different line segments, and there are additional informations which may required for kind of analysis. Like in this case, somebody may be interested that how much time does it take from reaching from place A to place B. So for that we need to have each of the segment of your whole path, and based on that we need to have some additional information that how much time generally people will take for each of those segments and to reach a destination. So these are basically data sets, machine data sets, and we organize it in broader in two categories. One is called geometry. So geometry is basically having a kind of the representations on spatial references like the point, line, and so on. And each of those geometry will have a few associated attributes. So like each point will have some kind of name. So like you're having a location A and B. So what you do is you provide an additional information. A is called actually an IRS, and it's, you can also put a starting addresses and so on. That can be conveyed back to the users. Similarly, you'll also have a different line segments, and those can also be added. So these combinations of these geometrical and attribute informations is, we call it the GIS spatial data. So to represent these GIS data sets, generally the geometrical part or the map data can be classified or can be categorized broadly in three different groups. One is called vector data, another one is raster, and the third one is basically a tin model. So tin model is a kind of three data representations, where vector is and rasters are a planimetric representation of any data sets. And all the attribute data sets can be added based on few keys which can be links to the geometry, and those attribute data can sit into any kind of databases. So these databases need not be restricted to only RDBMS datasets. This database can be a comma separated CSV file as well. So we can have an attribute information in a CSV file or maybe in a databases and so on. But we should have a kind of key using which we can connect these attribute informations to the map. So generally GIS data will be having some kind of representations where these two segments will be separated, and the connection and the common point between them will be a key. Apart from these informations about the map and databases, there is also some additional information is required for representation of GIS datasets. So these are called coordinate systems. So like whatever the lat long values we represent, so we need to have a kind of additional information like what kind of coordinate systems which we are having. Then there's also the scale and extent. So extent is basically telling, in theoretically we can say that we are having a space having an extent of in the infinite dimensions, in infinite distances. But to carry out a machine-based systems, there will be a limitation. So there has to have some kind of limited bounded geometry, and that's basically is being represented by extent. Then we need to also have a scale informations where we can do representations and so on. So these are the auxiliary informations which should be present in GIS dataset, so that whenever any analysis is being carried out, they gets an appropriate representations while doing an analysis. So from the previous slide, we see that there is a requirement to have a coordinate system. So coordinate systems are basically giving you starting and ending point. So it's basically a reference line, and origin is being set in. And these coordinate systems can be a projected one, or it can be a projected coordinate systems like WGS 84 based coordinate systems, or you may have a GCS based systems the way we are using the coordinate system which is being used by Google Earth and so on. So all these coordinate systems is going to be represented with respect to a local reference frame. So you need to have a reference frame, and then once you have decided that based on these reference plane and coordinate systems, you are going to have you are going to represent all the informations in that space. So space is being defined by the coordinate systems and the kind of local reference plane which is being used. And then on the top of that plane, we define different informations. So like we see if you talk about only a 2D representation of your data sets, then basically you deal with three different geometries, that point, line, and polygon. So once you have that coordinate reference systems, then you just draw or put your different features, spatial features, like in terms of geometrical, in terms of point, line, and polygons. So that's basically cases where the vector we are having a vector representations, and we are also having another representations called raster. So difference between these two we'll be dealing in detail in coming slides. But currently, the basic differences between the vector and raster is that vector is being used for discrete objects. So it means like in your spatial references, you'll be having a locations that will be marked, and it will have a fixed location X and Y. So you see in the vector representation in this case, the data is going to be represented by each of the point and those connection between those points. So that is being represented. So if you see, to represent these data sets, you don't need to specify each and every locations in case of vector data sets, rather than only the important feature segments or the important points which consists basically any kind of geometry. So you're having a point, so for the point you need to have a point. Then for lines, again you need to have a starting and end point, an intermediate point, then only you can define a line. So we can only store the intermediate points. And then similarly we can have a polygons, where we can just have a corner of these polygons. Apart from that, in the whole vector space, the other spaces are quite empty. So these are basically is being used for discrete data representations. But there are also another way of representing data sets, which is the giving the spatial reference with respect to in a whole plane. And these whole plane are basically is being divided at a regular interval. So what is being done in this case is that for each of those regular interval, a measurement is being carried out, and based on those measurements, the corresponding this cell, whatever cell we are having, that value is being assigned. So if somebody wants to store the data set in a raster format, so they will be storing the whole plane at a specific resolutions, or the size of each of those grid that will be present. And wherever there is no information available, so that's basically a no data value will be put. There's a specialized values. And in other cases, wherever values are there, so those values will get filled up based on the attribute of that informations. So raster data is generally is being used for representing the field data sets, where the vector data sets are being represented for discrete objects. Then to represent a 3D data models or 3D data sets, we are having a kind of tin model. So tin models are a kind of providing informations not only a space in 2D, but it also have coordinates in the z directions. So there are three of these coordinates are being used to represent each of the vertices, and based on that we get different furthermore geometries, like we have surfaces, or we may have a mesh representations and so on. So using that we can create a 3D surfaces. So this is just an example of how exactly the vector data is being stored. So on the right we see a kind of a reference plane, and on this reference plane of coordinate systems we have a point, a polygon, and a line. And line is basically consists of an intermediate nodes. So there's a starting point, an ending point, and in between you're having an nodes. In case of point, it will just be a locations, where in the polygons you have a starting point and then you move around, and finally it's a closed path, so it is coming back to the starting point. So that's how the polygon is being created. So this information gets represented in kind of tabular form, and these tabular forms you can think of that each of those points will have some kind of geometrical ID. So that will basically help us to distinguish which features we are trying to use it for representations. And for each of those points will have an locations or reference location x and y. So this is basically a point. So you are creating a set. In this case, the total 10 points are there to represent all these three features. So what you do, use this basic unit of 10 points, and you represents their x and y coordinate in this case. Then to represent a line, what you do is you just take a starting and ending point, and in between you also create an intermediate point list. So if you want to find out all the coordinates in the intermediate line, so what you do, you just take a starting, you take a line, you traverse it, you go at the beginning of the point. Based on that point, you get an xy locations. Then you start traveling all the node list starting from 1, then we have to travel to node 2, 3, 4, or finally we are ending at node 4. And that's how we'll be going through from the line which is represented by 1. So this basically says that if you are having a basic information of the points, then traversing that point, a set of points in appropriate order, you can create or you can represent a line. Similarly, you can also create a polygon. So polygons again is consist of a set of line traversing in appropriate order. So generally, any kind of vector data structures should have a kind of provisions where the individual unit of different geometrical features, that is point, has to be represented with its locations, and there has to have some kind of mechanisms where order of those points will have to be stored either to represent a line, and then polygons can also be represented as a order of the line in which we can traverse. So by representing these three informations or in a tabular structure format, we can have a basic data structures using which we can do a vector representations. So based on such representations, actually there are a lot of different models has been defined. So most simplistic model is called spaghetti models. So in the spaghetti model, what we do is we take different features, like we are having a feature A, that is a polygon, B and C. C is a line, and B is basically a point. So there are three different features are there. So all the nodes which will be which will be represented by each of those features is followed by the ID or the representation of that feature. So let's say an example in this case. So if you're having a polygon over here, so we say that this polygon is at A, and it's basically having a starting vertex and it is having an ending vertex. So you're having a two starting vertex and ending vertex, and in between we provide an order of the vertices list. So if somebody wants to create a complete polygon, so they needs to start it at the beginning of the file, then what is the starting vertex, start traversing in that order, and finally you end it at the same locations where you have started. So this is how you create a polygons. In case of a point is just consist of a single vertex. So it means like a point B is having just one vertex and its location is being provided. Similarly for a line, so this line is consist of an orderly traversal of the 4 points. So that is being represented over here. So line C is consist of 4 points, and each of those points coordinate has been represented in this case. So this is basically called spaghetti model. So in this case what happens is that all the information of all the geometries, like it's a coordinate or its nodes, its traversal order, it's an attribute, everything is being put it into a single file. And so it's basically a simple representation, so anyone can create this easily. We ourselves can create a simple text file, and based on that we can do a geometrical representations. So that's why it is very simple, and it is easy to manage. It is not having any kind of topology. So we'll come to these terms, to what exactly is the meaning of topologies. Then there is a lot of duplications, because in some cases, like in this case, we are having a starting node and ending node. So it means like these starting and ending node coordinates gets repeated. So that's why we are having a kind of duplications in this case. So similarly, if there will be a lot of duplications, let's say if you're having a boundary you're having a polygon A, and there's another area or another polygons just beside this A, then in that cases they will be sharing a common boundaries. So if you want to represent both the polygons, all these sharing coordinates and line has to be repeated. That's why there will be a lot of duplications in this. And it's so these are the basically a demerit of that, and mostly it's earlier it used to be part of any kind of CAD based systems. So due to that duplications and a lot of cluttering, the people have slightly modified these representation of these data structures, and then they have separated basically two parts. So one is, in case of repetitions, all the vertices which is being used to represent any kind of geometries are being put in a single file. So as we have seen in the earlier tabular structure, so you're having a file which consists of vertices or the point IDs and its corresponding location. So these are the file which just contains the all the locations which is present, and there is a second file which basically represents that in which order and what is the orderliness of these different vertices to achieve a polygon or a point or a line. So that is being represented in this case. Then we are also having a certain additional informations or another format which is called a DIME, so dual independent map encoding. So it is having a very similar structure like this, whatever we have a vertex dictionary, but along with that it also have some additional information. So this additional information basically gives the kind of representation. So representation in terms of spatial relationship. So these spatial relationship, like a polygon A and B, there are two polygon. There's a polygon A, and there is also an external polygons which is outer world from this coordinate system. So that can be considered another polygons. So in this case, what happens is that the spatial relationship, especially that there is a left or right, or what are the other polygons which is present on the left side or the right side of this polygons, is being stored. So this storage of these informations basically brings up the concept of topologies. So topologies are basically uh, uh, a kind of spatial relationship which is not going to change with respect to any kind of transformations which you do it on the plane. So, but still the relationship will exist. For example, if one polygon is there and whatever transformation you do a different projection system changes from one 3D geometrical representation of Earth to a 2D projected representations. But different districts, whatever we have, the neighboring districts positions is not going to change. So it means like if a district A is there, then corresponding neighboring district B will always remain to left, whatever representation or projection systems you do it geometrically. So these kind of informations are being stored, and these are called a topological relationship, and this becomes an important informations for carrying out directional analysis. Then uh, the the topological relationship are can be represented in few of the commercial software like ArcGIS, which is using an arc model. So in this case, what happens is that you have an arc geometry. So basically, you call it, or it's also you can consider it to be a line. So there will be a starting point and ending point. So starting point and ending point, and in between the vertex geometries. That's what we do it. So this is basically only storing the different lines, different arc or lines, and then we also stores as the diamond stores the polygons in the previous cases. In this case, the relationship or special relationship of each of those lines is also being stored with respect to other polygons. Like you're having an arc or a line geometry over here. So this is arc 1, arc 2, and arc 3. And in arc 3 is a simple line like this. So on this line, on the on the left side there is a polygons called C. On the right side there's a polygon on external polygons, and so on. So these kind of information get stored, and that's what we call it the arc topology. So you are having an arc topologies which gives the relationship of any line segments to its neighbor geometry. We can also have a polygon geometries. So that's basically a polygon based, as I was telling, the district if you want to represent. So there will be a representation of a district A and what is the neighboring district B. So both the relationship which district is on the left side of this or right side of this, that kind of informations can be stored in a polygon topologies. So these are the 4 different files which has to be present for or which is present in ARC model or E0 file formats. So that was basically a proprietary format, but later on what has happened is that OGC has taken up different file formats. They have seen spaghetti models, topological models, and so on. So considering that variety of different data representations, finally what has been done is that there was some kind of consensus that is being brought it into a different kind of models, so that if some software is using, let's say, a spaghetti model, another one is using an topological models, and if we wants to do a conversion from one software to another software, then we need to have some kind of representation of that how geometry is being represented. So Open Geospatial Consortium or OGCs has provided a simple feature models. So what they have done is they have taken all the geometrical objects, and these geometrical objects has first been categorized into 4 groups. So 3 groups, the basic geometry is like point, line, polygon. So that are the basic groups which is being provided. And then we are having a multi geometry collections, or it's basically a geometrical collections. In the geometrical collections, we can have an homogeneous classes, or we can have a different kind of classes. Homogeneous classes means we can we can say that a couple of a bunch of lines being called as a let's say path for cycling path in a particular administrative area. So we are having a few paths, and or the different paths, so that can be put it as a collections. So different paths will be grouped together and we can say the walking path in, let's say, in IRS and so on. So that kind of a similar kind of multi collections can be there, or there can also be a set of heterogeneous classes. And in this case, basically, there are a lot of few details has been provided, like how we can distinguish a class or subclass and so on. So few of the flags is being flag has been provided. So those are basically called subclass of geometries. And then again, there will be a planimetric geometry. Some geometry may be their attribute may be there, but positions may not be defined and so on. And in this case, basically, the topological part are also being defined in basic geometrical class. So if you say that in geometrical class generally, or the geometrical class, whatever OGC has defined, so it should have a kind of spatial referencing system. So as we have seen earlier, that you need to have some kind of origin and the reference scale. So that's what is being provided by the spatial reference systems. Then the kind of geometries, so there are line, point, polygons, and along with that we are having a line strings. So that is basically a set of line strings. So like in the road, maybe consist of a multiple segments having a lot of turns, left and right turns and so on. But still all of them will consist, all those segments, line segments consist a road. So those are is being represented as a line string. Or we can also have a polygons which will called a line ring. So generally we can have polygon within a polygon. So that kind of line rings can be provided. So these are basically a planar geometries. The collection geometries are multi-point, line string, and multi-polygons, which is being there. So all these geometrical classes are supposed to have a representation of spatial relationship, so that these spatial analysis can be carried out in the spatial objects. So I think we are clear about the basic geometry, what exactly point, line, and polygons. I'm just trying to in this slide I'm trying to say what exactly and how the different kind of geometrical collections is being defined. So there can be a single uniform collections, like point collection of point or lines. So like you're having a lot of points here. So all these points, let's say we call it that each of those points are basically a food locations where somebody can get. So we can say a set of food codes available within a IRS and so on. Similarly, we are having a lot of paths. So these paths collectively is called a cycle path. But still each of those lines have its own representation. So this is basically a multi line. Similarly, we can have a department may have multiple buildings. So all the 4 buildings can be called unifiedly as a single department. So in this case, we see that there is a geometry of collections of a single type only. So you are having a lot of points, either points or a set or a group of lines or a group of polygons. So these are basically a single type polygons which we are having. This is also called an homogeneous polygons. And then we are having a heterogeneous collections where it may consist of a polygon, line, and point combined together. So we can call it a particular departmental areas which will have a few landmarks, buildings, and paths. So all of them can be grouped together. So this is basically an heterogeneous geometrical collections. So OGC provides the kind of data structure where such kind of heterogeneous geometrical collections can also be represented. So that was basically a vector data representation. So now we'll see the raster data representation. So generally in the raster data representation, as I said, that in this case there are different points, and a group of points or those group of points can be called as a grid. So each grid points basically going to represent or going to cover the whole area. And in the raster cases, what we'll have is that for each of those grid points, we'll have a few defined values. Like in this case, at location 8, 6, we are having a value defined as 46. So these values can be anything, like in case of remote sensing images, you might have seen that is it can represent a simple radiance values getting converted into DN numbers, and that's what we call it as satellite images. Similarly, we can also represent or take a grid, and we can do a classifications, and based on that the location 46 or the value 46 may represent a particular class, or it may be outcome of some GIS analysis like distances from a specific locations and so on. So it can be any kind of functions which will be dependent upon on the each of those grid locations. So this in these cases you'll be having a column number and the row numbers, and based on that column and row numbers we are going to have a value represented in this case. In this case, what happens is that each of those locations are at fixed distances, and the distances between them is also called pixel resolutions of the raster grid systems. And then we are having and there are few properties of these representation. Like in the previous case, any kind of neighborhood data we need to store it. That is a topological information we need to store it in case of vector data sets, where in case of raster data sets the topology is already built in this grid structure. So if somebody wants to, let's say somebody asks like which cell is at the left side or the right side of the 5,4. So we know that from the 5,4 we have to go into 5,5 location. So on the left hand side we'll just move one unit and will be on the left side. Similarly, if you want to go on the north, east and north side and so on. So there are fixed topological relationship is already existing between these raster grid data structures, and in these cases we don't explicitly need to represent this topological relationship, because in the grid structure this topological relationship is already inbuilt. And generally, it's whenever we do a representations, the most of the software assumes that the value which is being represented by this whole grid can be considered to be concentrated at this point location, and this becomes an important factor to consider whenever we do any kind of analysis. We need to know how the software is basically representing that point. Some cases what may happen is that your point may be considered to be located at the crossing of these grids. So if you're having a two data sets where one format represents the data to be at the center location, another one is considering to be represented at the a kind of corner one, then these offset values has to be taken into consideration while analysis. But most of the GIS software whatever we use, generally whenever we do any kind of fixed conversion, let's say in a GeoTIFF, and all the files are of GeoTIFF format or IMG format and so on. So in those cases that differences or the locations of the values it doesn't becomes a problem at cases. But while conversions we have to be very careful. And one important aspect of these kind of grid system is also there, that in this case the reference point of or the location of all these points are not getting stored. In this case what happens is that the origin of a locations will be defined. So it means like the starting point of the locations will be given, and then since this is a planimetric representation, so we know that how much unit distance we need to move it to the another location. So each of those point locations are not getting stored in your file, but rather than is being derived based on the structure, that is the fixed distances which is being provided, and that gets computed. So that brings us slightly differences. Like in case of vector data sets, we need to have a representation of each of the point locations, as we have seen earlier, that each of those point has to have a particular coordinate systems. Where in case of raster grid, what happens is you store only the geometric or the geospatial lat long value referencing at the origin, and then there is a fixed distances between these grid points. So we just need to traverse in a particular directions, and we'll come to know what exactly is the location. So let's say if I want to find out the what exactly is the lat long value at 1,5, So if I know that origin is, let's say, at 78, 280, and each of these is, let's say, at the 5.5 degree, so we know that we need to reach to this point, we need to travel 1.5 degree units. So based on that 78, I'm like, we'll having a 78 degree plus 1.5 will add, so 79.5 and then 38 degrees. So that is the basically values or the coordinate systems we can easily derive it. And that's how the raster grid systems is being created. So in the raster grids, data is being, the value is considered to be located here, but on the representations, it basically considers that this occupies the whole grid. The impact of that is that whenever we do a visual representations, that the smoothness of your geometry, whatever you had, now that will no longer will be existing, but rather than it will get lost, and the information will look like a collection or a sequence of grid points. Like in this case, there was there's a point which is located at the this grid point, but after rasterization process, this point is now supposed to be available within this grid. So this is basically a slight differences where smoothness of your geometry is getting lost, and the smoothness will depend upon how fine your grid size is there. So that's basically we have to keep in mind whenever we do a raster data representation. So this is just an example of the impact of rasterization process. So we're having a line, and whenever we carry out that rasterization, so we see that there's a jagged effect. Then there may be also be cases where in one cases we may be having a geometry quite smooth, but after conversions you see that there are a lot of smaller polygons has now almost is being disappearing in this case, because the total area of this particular polygon, the smaller polygons, maybe the smaller is lesser than the total area of a grid size. So due to that, there's an information loss is possible in whenever you are doing any kind of rasterization processes, but still it is being used because analysis on doing on raster is quite easy, and so it's basically you need to have a simple map algebra, that is basically a unit doing some two layers and adding it in a matrix forms that can be resulted. So still the raster is being used. And second one is the kind of requirement we have. Like sometimes we need to have a representation of the field based data. For example, if you want to represent a temperatures, then we represent a temperature in the whole area. So locations can be represented as a point, but if you want to represent a fields kind of phenomenons, then in those cases we need to have a raster data is important. So as the raster data is going to contain the information for each of the grids, so there are few compression techniques is been applied, because in the raster cases it stores a lot of information. In case of vector data sets, they need to install or store the informations based on the geometry whatever we have, but in case of raster, apart from the basic features, we also need to store the other grid pixels values and so on. So due to that, there's a possibility that in your data, whatever the raster data you have, the size of that file might be quite big, even your information is taking a very smaller portion in the whole extent. So to overcome that, what has been done is that there are a lot of compression techniques has been applied. So this basically represents 4 different compression techniques. One is called run length encoding techniques. So in the run length encoding techniques, what happens is that in a serial manner, you just take a starting point and you see how many times it is getting repeated. So let's say in this case, we are having an A which is repeated 6 times. Then similarly, we are having a B which is repeating 4 times, and we are having a C which is representing which is repeated 9 times. So in this case, if you see, there are total 19 different values, 19 different grid values are being represented over here, and each of those, if we represent in a file, then it is going to take a some amount of storage space. So in this case, there's a 19 multiplied by the amount of storage informations to store a particular character, let's say A. So there are that many times is there. But if you just represent it based on the compressions, so we just simply decode it, like we are first encoding it, that's 6 times A followed by 4 times B and 9C. So the whole 19 different character which was storing and having a lot of repeatability has now been compressed into representations of only 6 different characters. So this is basically called run length encoding. So and that's being applied. So in this case, just an example that it is basically a row-wise run length encoding. So at the first row we are having no informations. So it means like no information means 0 is repeated 8 times. In the second row we are having 0 is repeating 4 times. Then red color feature that is being represented as 1 is repeating 3 times. And finally then another one is the 0 is repeated again, is being represented 1 and so times. So in this case we see that for each of those rows how many times this value is getting repeated, and that's how this whole informations is being compressed. And due to that, instead of storing 64 different values, now information what is being represented over here is quite less compared to the total storage is being done. So this is basically a run length encodings. Similarly, there's also a chain length encoding. So what happens is in run length encoding, whatever information we have, no data information is also getting repeated for each of those rows. But in case of chain encoding, only the relevant information and the outer boundary is being stored. That's what is being shown over here, like it is the starting point of 5, 2. Then in the eastward we need to move 3 grid size, then again we have to come back on the south direction 4 grid size, then on the western side 1 grid, come again south side, and the western side again north side, and so on. So what we do is basically we give a directional informations that on the outer boundaries of these features, and that is getting stored. So this is basically called chain encoding. Then we are having another representations called block encoding. So what in this case is being done is that we look for a maximum size block in the cases, and then we go smaller and smaller size. Like in this case the biggest block is 3 by 3, that is a block size 9. Then we take 2 by 2, and then finally 1, 1. So this whole geometries can be represented one very large big blocks, 2 medium size block, and 4 smaller unit blocks. So that is being represented over here, and this is called a block encoding. Then the other encoding technique which is called a quadratary encoding, and this is quite widely used in different raster data representations. So in this case what happens is that whole geometry is being divided into homogeneous group, and these homogeneous groups has to be a kind of the maximum blocks size where the homogeneity remains and does not heterogeneity is completely 0 and homogeneity has been achieved. So the subdivision of the whole blocks gets stops. Like in this case the whole block is being divided into 4 parts, but on the northwest side and southeast side we have reached to a homogeneous representation in orange and green red color, and there exactly we stops it here. But in the case of eastern side, eastern northeast side and southwest side, we are having a still homogeneity has not been achieved. So there's a further division is being carried out. So that's what the level 1, level 2 and so on, that kind of representation is being put in. So this is just an example of different raster data compression which is being carried out to reduce the amount of informations which is getting stored in a file. So just to summarize that, what are the different differences between raster and vector data sets? So it's basically a vector data set is a kind of discrete object-based model, where raster is a cell-based models. Positions of each of those point has to be stored, and it can also be a fractionals, where raster data sets the information is considered to be located at specific location. So fractional information is not being considered over here. The vector data sets generally take a lesser space because you are having a very less amount of information in terms of nodes compared to raster, which covers the whole space. Then we're having the representation of vector data sets will be an basic geometry, that is point, line and polygons. And in raster, the basic geometry or the unit is basically a cell. This is, and mostly in the vector data sets, we carry out the geometrical based analysis. So that is also called a vector analysis. So we'll just see in the coming days that how does the vector analysis being carried out. In this case, basically a geometrical based operation is being carried out. So you take two geometry shapes and look for overlap and so on, and that's based on that can be done. Where in case of raster data sets, the grid is fixed. You need to only carry out the addition, subtraction and so on. That's basically, it's a basic algebraic informations are there. All the points which is consist of all the points which is present is being used in the vector data sets are referenced, where in case of raster you have only a origin with reference and the remaining cells can be computed because the size of the each cell is fixed and distance is being done. And there are a lot of different format in vector like E0, SHP, KML, KMZ and so on. So these are basically a vector data formats, where in case of raster, geotape, Faradas, IMG and so on, HDF formats and so on. So these are the different file formats which is present. To represent a 3D, we have a very simplistic model that is called a network model. So again, this is basically you're having a node location x, y. Along with that, you also provide a z. So that is basically, and height is also being represented for that. And based on that, you create a node list. And then what is being done is that to create a mesh or surface, there is a kind of triangulations is being carried out. So based on these triangles is being created in such a way that there is no overlap between different triangles, and the distances between these points are actually equal, and all of these points are supposed to lie on a single circle. So that's how all these coordinates of a triangle are considered to be located on a same circle. So there are few constraints being put. So that basically ensures that you create a mesh, and that mesh triangulations leads to a kind of faces which is being created. So this is basically a face A consists of different vertices in the direction, like in A vertex A is consist of 3, 2 and 6 node, and whatever the neighbors is there, that is also getting stored. So this is very simplistic representation of tin or triangular irregular network that is being used, and that's basically help us to create a kind of representation like this, or 3D model like this. So in the cases of triangle model, you have nodes, and then you're having a different edges, and then for each of those nodes you have a corresponding Z and Y and locations which is getting stored. So generally 3D tin models are basically used for 3 data sets. It's basically a triangle based, especially it follows the Delaunay triangulations constraints, and then the triangle height can be computed based on the interpolation. So we can carry out and try to find out, let's say at a distance we want to find out what exactly a distance at these locations. So taking an appropriate weightage of these nodes, the value at these locations can be computed, and all the node heights are also stored. So it means like the locations of the points are getting stored in this case. Apart from that, there are also another way of representing spatio-temporal information. So apart from geometrical informations, the temporal information also gets stored. So in this case, one is called a snapshot model. So you have an spatial referencing geometry, and then you attach an additional temporal attribute to it, and then you say that this representation is for this time and so on. So this is called a snapshot based model. That basically means that at a particular instance of time t1, what was the state that is getting stored. This is basically a raster representations. Similarly, we can have a vector representations where we can say which of the polygons was present at all the time, which was present at time 2, time 3. So basically that's basically you need to have a cross tables available to you, and that's how this is the spatial time composites can be created. We can also have a vector based models where we can see evolutions of a specific polygon, how it is getting changed. So we are having one representations where we are having a two geometries. Later on, as the time has progressed in z directions, the polygon has again broken down into smaller segments and so on. So that's basically an ST or spatial time object based model. So that's basically helps to put in irregular models. In a snapshot based model, most widely used, especially using the classification of satellite imagery. So you have different satellite imagery having a different time frames, and based on that time frames you do a classifications, and you'll come to know what was the LULC classification or LULC present at a particular time, and that's being represented over here. Then the special just to see that what exactly is the topological relationship. So this basically gives the kind of some property which doesn't change with respect to any kind of transformation. So that's basically the spatial relationship which is being represented by your topologies. So generally, if you see that these are the 8 different spatial relationships which exist. It's basically there's no connections between any points or two polygons or two features basically meeting at a point. One polygon is completely covering the another area, one is inside the other. So like inside can be example of that. The outer red can represent a country where the smaller polygons can represent a state. So we can say state is always has to should be within the one particular state can be within the country and so on. So similarly, we are having containment, covers, and others. So these are the basically different kind of spatial relationship, and these spatial relationship are supposed to be invariant to any kind of uh, basically transformations. So whatever relationship we have, if these two polygons are there connected at these nodes, so whatever transformation, stretching or shearing we do on these geometries, these connections node will always will remains, and that's the basically spatial relationship we have, which we represented using an topological relationship as we have seen earlier. So in this case, you take an starting and end point, and then finally you just represent point A and B, and whatever the polygons are there, just mark on the arc on a particular arc what is the polygon, which polygon is on the left side and which polygon is on the right side, that can be represented. So this is just an example of the different file formats. This is one of the examples which you generally find it in proprietary software like ArcGIS, which will have a personal geodata sets, it will have a set of feature data sets which shares a common reference systems and all, and then finally you'll be having different kind of geometries. Similarly, we can have different coverages. We can also have network based topologies. In the arc, coverages are also is being represented over is being shown here, and we are also having a shape file. So this basically represents or shows the different kind of file format which is existing in a proprietary software like ArcGIS. This is just a directory structure, so that's basically a logical organization which you'll view in ArcGIS catalogs, and this is basically a file representations which will be there in that folders. So this is basically a containment of giving informations of that feature data sets will have a common spatial referencing system, different kind of objects, relationship or topological relationship, especially the planar or network topologies. These two are also stored, and there are also a validations rule which basically says that these validations rules are applied on these topologies to find out the different constraints. Then in the same geodatabase, you can also store the raster, you can also store the tin, and then we can also store a few locators, and that's basically a specialized points reference which can be used apart from giving a positional informations for other tick points and so on can be stored. Recently, we are also seeing a usage of GeoJSON format. So it's basically represented, each geometry is being represented with features, objects. Then there are feature objects with multi-point line polygons. It's basically a collections, homogeneous collection, heterogeneous collections, and basic geometry. So all these are called geometrical objects, and these geometrical objects will have few attributes. So combination of these two is going to give you a feature objects or feature collections. That's how the data representation is there. The attribute informations is being stored in form of flat files or relational databases. So there are different databases are there, and that databases stores all these the information or the attribute informations, and there are different ways of representing. So flat file format, as I said, like you can store a simply CSV file, and you can have a reference to a geometry ID. Similarly, there are hierarchical models and so on. So these are the different kind of models based on the database technologies which is being used. So generally, in case of attribute informations, you are going to represent tabular structures which will have a kind of keys. These keys is going to links to your geometry, and that's what you see over here. So you're having a geometrical informations and you have attribute informations, and combinations of these is going to give you established relationship that these polygons, what it names and so on, that can be stored. And this is basically called a relational algebra based organizations, and using these relational algebra based organizations we can carry out the spatial queries like select or aggregations and so on. Those kind of things can be computed. So I'll be just breaking now, and after break I'll just take a couple of questions. If it is any questions are there, you can just post those questions.